I'm in the video right now?
Yes, all right, guys, got a guest speaker. We are getting ready to start a unit, sequences and series, which is a very important topic in BC Calculus, and you're going to need to know what this big sigma thingy means and what sequences are. But anyway, there's a BC Calculus student here to give you a shout out. She wants to be in the video, so here she is.
If you see Susan Nguyen, you tell her that she missed out on being in this video, but Diana was.
Okay. Bye, Diana.
Bye.
Okay, so anyway, we're going to go over this, but before I do that, I want to give a shout out to my little table of studettes in first period. And that table has got my two Ninas and my Nima and my Sidal. And Sidal is also called Honey Badger Sidal. You would know why she's called Honey Badger if you were an administrator that tried to stop her in the hall, because she does what she wants. Anyway, so there's your shout out. So here we go. We're going to do some sequences. I'm going to talk to you about both explicitly defined and recursively defined. I'm going to show you how to deal with them. We're going to do an example, first of all, of an explicitly defined sequence. Now, for a sequence, they have a domain of the set of all natural numbers, which means that we're going to start with 1 and go as far as you want. You can go all the way out to infinity, but we're not going to define them. We won't have numbers like 0 or -1 or -2 with them. So sequences start with the first term and go to the second term, and they go to the third terms. And it's a list, and it's an ordered list. You cannot switch things because the sequence has to have a pattern, and if you switch the list around it doesn't have a pattern anymore. So let me give you an example of an explicitly defined sequence. Here is a sequence O, T, T, F, F. Now I want you to pause for just a second and see if you can figure out what my next letter is. So go ahead and pause, and I want you to see if you can figure out what my next letter is. Okay, so I hope you paused that. Your next letter is an S, and then the letter after that is an S. Now I want you to pause again and see if you can figure out the next one. Okay, I hope you're back. The next letter is an E. So if you know this pattern, pat yourself on the back. This pattern is the first letter of the numbers in order. We start with 1, and the way you spell 1 is O-N-E. So O is the first one, and then we're going to call this A sub 1 because it's the first term in our sequence. The second term in our sequence is a T because the second number, we'll just do T-W-O. The second number is 2, and it starts with T, and we're going to call that A sub 2. And the third item in our sequence is T because the third number is 3, and we're going to call that A sub 3. Do you see the pattern now? This is F because that's the first letter of 4, F because that's the first letter of 5, 6, 7, 8. So if you don't know it by now, you need to seek help from somebody else and come in for tutoring or something. But the next one would be a N. So, and these go A sub 1, A sub 2, A sub 3, dot, 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 all the way out here. That's A sub 9 because that's the 9th term. So let me tell you why I say this is explicitly defined. Let's say if I went all the way out to A sub 75. Could you tell me what letter goes in place of the A sub 75? Well, sure you could, because you know that 75, the first number is a 7, and how you spell 7 is with the letter S. And so you know just from that information you could tell me what that position was, what's A sub 75. What is A sub 192? Well, that would be an O because you spell out 192. That's an example of an explicitly defined sequence. You can find any part just by knowing the number or the position in the sequence. This is very, very important also for SAT. This will really help you with several of those questions. So now let me give you an example of a recursively defined sequence. This one is not explicitly defined. So like 1, and then 1, 1, and then 2, 1, and then 1, 2, and then 1, 1. This is a recursively defined sequence. I want you to stop and pause and see if you can figure out what it is. All right, the next term would be 1, 1, 1, 2, and then 2, 1. This is a recursively defined sequence because each term describes the term before it. Now let me explain to you what this looks like. The first term is 1. The second term depends on or explains the one before it. The second term says there's 1 in the term before that. There is 1 in the term before me. The term after that describes the one before it. The term after that says that there are 2 1s in the term before me. This has nothing to do with the first term, but it's just saying it's describing the term before it. And then the next term says there's 1 2 in the term before me, and then 1 1 in the term before me. And then the next one is that says that there's 1 1, and then there's 1 2, and then there are 2 1s. So let's see if we can figure out this next term. The next term would be 3 1 because there's 3 1s, and then there are 2 2s, and then there are 1 1. So in these terms, a sub 1, a sub 2, a sub 3, a sub 4, ... could you tell me automatically what a sub 75 was? Well, of course you couldn't, because you need to know the term before that, a sub 74. You would need to see that to be able to tell me a sub 75. And so the way a recursively defined sequence looks is it has something like a sub n is some version of the term before it, a sub n minus 1. Notice a sub n minus 1 is 1 less than n. So to know a sub 75, you would need to know something about a sub 74. And there will be like some coefficient in front of it. I'll just put a c there. So it's some constant times that, or it tells you what to do with the term before it. I'll give you an example of that when we go through here. So let's just go do a few examples of some sequences. So let's have a sequence, a sub n, that is defined by n plus 1. And let's write the first 4 terms and then the 100th term. Now the first 4 terms, nice spelling there, Mr. G, the first 4 terms and then the 100th term. All right, the first 4 terms are a sub 1, a sub 2, a sub 3, and a sub 4. And the way you get those terms is you have this formula. A sub 1 would equal, you plug in the 1 for n, 1 plus 1. Well, that's 2. And then a sub 2 would be n plus 1, where your n is the little subscript. That's 2 plus 1, and that would be 3. A sub 3 is 3 plus 1, which is 4. And a sub 4 is 4 plus 1, which is 5. There's the first 4 terms. We plug in, start with 1, because that's the first natural number, and you plug it in for n, and you figure out what that is. The 100th term would be a sub 100, which would be 100 plus 1. So the 100th term is 101. So that's an explicitly defined function, and that's how you generate the list. You start with 1 and you plug it into the formula and you just list out the numbers, and it just keeps going. Alright, now let's do a recursive defined sequence, one that depends on the one before it. So let's take a look at this little formula. Let's do an example of a recursive defined sequence. Alright, so let's have a sub n equals 2 times a sub n minus 1 minus 2. And you always have to have something to start with, and here we're going to have a sub 1 equals 3. So let's find the first 5 terms. Alright, so that means that I need to come up with a list that looks like this. A sub 1, comma, a sub 2, comma, a sub 3, comma, a sub 4, and then comma a sub 5. Well, a sub 1 is given to me. I know that first one is 3. But how am I going to find a sub 2? I'm going to use this formula. This formula says if you want to find a sub anything, you, in parentheses, you do the one before it minus 2 and double that. So for example, a sub 2 could be found by doing 2 times parentheses a sub 2 minus 1 minus 2. So a sub 2 is 2 times. A sub n minus 1 is the term before it, or a sub 1 minus 2. So you see how these are related here? A sub 2 is 1 more than a sub 1, just like a sub n is 1 more than a sub n minus 1. So this means the term before this one. So since a sub 1 is 3, then a sub 2 is 2 times 3 minus 2, which gives me 2 times 1, which is 2. So it's subtract 2 from the one before it and double that. So let's see if we can't find a sub 3 then. A sub 3 would be 2 times the one before it minus 2, which would be 0. And then a sub 4 would be 2 times the number before minus 2, which would give me negative 4. And then a sub 5 is equal to 2 times the number before it minus 2. That's negative 6, that's negative 12. So let's see how this was recursively defined. You take the number before, subtract 2, and double it. So the way we get to a sub 2 is we take 3 minus 2, which is 1, and double it. Then the way we get the next term is we do this term minus 2 and double it. This term minus 2 and double it. This is a recursively defined sequence. And notice I could not ask you to find a sub 50 because I would need to know a sub 49 to get that. All right, I want to show you that a graphing calculator is going to be helpful for this, especially if we want like the first 1,000 terms and we don't want to plug, we don't want to do 1,000 algebraic statements. So I want to show you on the calculator how to do this, and you'll have to do this on your homework. What we're going to do is we're going to go to mode on our calculator, and we're going to go down until we see function, and we're going to go all the way over to SEQ. Guess what that stands for? That stands for sequence. Then when you go to y equals, you're going to want, by default, it should be at n minimum. It should be at 1. And what we're going to do is we're going to type in our equation for our u sub n. And so we're going to define this u sub n. I need to come back up here to u sub n. We're going to define this as whatever this formula is. I think earlier we did, well, I don't even remember what we did earlier, but I'll show you what we're going to put here. We are going to put 4n plus 3 in for u sub n. And so when I do 4, when I press my X button and n pops up, plus 3. And I'm going to find the first 10 terms by using my calculator. So I'm going to go to my window, n minimum starting at 1, n max is 10. That's the first 10 terms. And I need to figure out my x min and x max. X min is going to be negative 1 because I like to see the y-axis. My x max is going to be 15. And then my y minimum is negative 1. My y maximum is going to be, what happens if we plug in 10 for n? We're going to get 43, so I'm going to need to see all the way up to at least 45. And I can actually graph a sequence. And you can see that the sequence is only defined for those natural numbers. And so we have a graph of the sequence. So you can find them by going to the table. And if you go to the table, it's waiting here. Oh, my table's way up there at 79. Go to my table set and tell it to start at 1. And there we go. So let's go back there again. You can go to the table and it will generate the first however many terms for you, and you can also graph them. So you'll have to do that as well. Now the last thing we're going to do is look at a list and see if we can't go backwards to the formula. So let's do that one at last. So we're going to do what's called find the nth term, and that's just simply finding the formula. So let's find the nth term, and this will be a little creative. You're going to have to try a few things. So let's start with something simple. I'm going to have a list 2, 4, 8, 16, and you're going to have to notice a pattern. What are these numbers? Let's see, am I adding something? 2 plus 2 is 4, but then 4 plus 4 is 8. So it's not a common adding. You're like, wait a minute, that looks familiar. Those are powers of 2. So your a sub n is your doubling function, or 2 to the n. Let's make sure this is right. Plug 1 in for n, you get 2 to the first. Is our first term 2? Yes. Plug in 2 for n. What do you get? 2 squared. 4. So whenever I plug in 1 for your formula, I better get the first term. And when I plug in 2 to your formula, I better get the second term, and the third term, and fourth term, and on and on and on, like that. Let's take a look at another one. Let's take a look at another example, like 3/4 and then 4/5 and then 5 over 6, and then 6 over 7. Now we can see that these are fractions, so my a sub n is going to have a fraction. And the top numbers are going 3, 4, 5, 6, and the bottom numbers are 4, 5, 6, 7. So the bottom numbers are 1 more than the top. So what we have to do is come up with a formula that when I plug in 1 for it, I get 3 on the top and 4 on the bottom. And I have a common slope of 1. That means my top equation and bottom equation are going to have a 1 in front of their n. I know that for sure. What I have to do now is figure out what do I do with it after I've multiplied by 1. See, a sub 1 is equal to 3. If I plug in 1 for n, 1 times 1 is 1. What do I have to do to that to get the 3? I have to add 2. And then on the bottom a sub 1, I've got a 4 there. If I plug in 1 for n, 1 times 1 is 1. I've got to add 3 to that. And so my formula is n plus 2 divided by n plus 3. All right, so you guys are going to practice all of these examples in class on Tuesday, and I will see you guys then.